Good evening, everyone. Welcome to Astronomy Night. My name is Dylan. I'll be presenting for you, and this is the brief history of the universe. Before I begin, I just want to thank Julia and David, my partners back there, for helping this presentation come to be. Without further ado, let's get started. Can we take this back to the beginning, please? But what is the beginning? The beginning of, well, everything, of the universe. Well, the beginning is defined by the Oxford English Dictionary as the point in time or space at which something starts. Now there's the problem. We don't exactly know when or where the universe began. In fact, we don't even know why. All we know is that at some point in time, 13.7 billion years ago, there was nothing. There was nothing at all. There was no light. There was no you. There was no me. No Earth, no universe. But there was potential in one extremely tiny point. And then one day, that point expanded, and the Big Bang happened. And the whole universe expanded and continued to expand. But the Big Bang really isn't a good name for what happened because it wasn't big, and there was no bang. Now I say it wasn't big because, as I mentioned, it started from one extremely tiny point. Now how tiny is that point? Well, this point is tinier than an atom. It's tinier than an electron. So how can we say that that was big? Now let's address the bang. Well, at this point in time there was no air, so there could be no sound vibrations, so no bang. So the name really didn't fit what happened, but it stuck. So like I said, Big Bang happens, universe expands and continues to expand. Now, we all know who this is, Albert Einstein, marvelous scientific mind. Now, he came up with the theory of general relativity, which is an important theory, but the reason it's relevant to this presentation is because it stumped him. And it stumped him because, in order for his theory to be correct, that must mean that the universe is either contracting or it's expanding like it was, but he couldn't figure it out. He couldn't observe an expansion or contraction. So he had to just throw his hands up and go, well, I don't know the answer. 1929 rolls around, and here's Edwin Hubble, and he discovers that the galaxies are moving away. And he discovers that through something called redshift. Now, he was here on Earth, he's the observer, and he was looking at galaxies, the source, distant in space. Now, when you look at something far away in space, you analyze the light. And when you see the wavelengths, if they're longer and appear redshifted in the spectrum, that means that that source that you're looking at is moving further away from you. Contrary, if the wavelengths are shorter and it's shifted to the blue end of the spectrum, that means that that object is moving towards you. Now, all the hundreds of galaxies Hubble viewed were all redshifted. They were all moving away. So, therefore, everything in the universe is moving away. But he didn't just stop there. Even though this was enough to make him famous in the scientific community, he didn't stop there, though. He discovers that the universe is not only moving away, but it's expanding. Because as things are moving, he notices as they move further and further away, they pick up velocity and begin to expand more and more. So instead of just moving like this, they begin expanding as they move, and the universe gets bigger and bigger and bigger as time goes on. And Albert Einstein was amazed by Hubble's discovery. Now here we have again the expansion. Hubble proved that this was happening. Now, what if we stop time and roll it back? Shouldn't that mean that everything contracts? Contracts to one tiny point? That singularity I was talking about? Now, I've given you, most of you should have one, I've given you a Post-it note. What I want you to do is fold this Post-it note in half and continue to fold it in half until you can't fold it anymore. And I'll do it with you. Alright. Feel good? Okay. So this is how small I was able to get mine. It's a lot smaller than it was, and it's a lot harder, it's a lot denser than when it began, because I crammed all this space into a smaller area. Now let's think of that on a larger scale. On the scale of the entire universe. Everything in the universe. Not crammed into something this small, but crammed into a point smaller than an atom and an electron. Think of everything in the universe. All the galaxies, all the planets, all the stars, in a one tiny point. You think this got hard? This point was infinitely hard and dense. Not only was it infinitely dense, it was infinitely hot, because what happens? You look up in the night sky and you see stars. Those stars are made of heat, which is energy. And that energy is also within that one point. Not only the energy from stars, the energy from everything in the universe is in that one point. So it was infinitely hot because of the energy, and it was infinitely dense. So as I mentioned, it expanded, and expanded quickly. Now, what that's known as is inflation. And this expansion happened within a billionth of a trillionth of a trillionth of a second. The universe doubled in size at least 90 times. So doubled once, doubled 2 times, doubled 90 times. That's incomprehensible in such a fraction of a second. Now, not only was the universe expanding during this time, the forces were getting broken down. The superforce divides into the electroweak force, the strong force, and gravity. Strong force and gravity stay the same, but electroweak breaks off into electromagnetism and weak force. Now, as I mentioned, it is so hot right now. It's in fact so hot that mass and energy can't decide if they want to be 2 different things or 1. So right now, they are 1. So let's move 3 minutes after the Big Bang. Finally, things have cooled down. And I use that word lightly because it's cooled down to about 1 billion degrees. But this is just enough cooling to allow mass and energy to divide into 2 separate entities and to allow hydrogen and helium nuclei to form, which will be very important later on. Now, what have we been talking about so far? This is part of a larger picture called the radiation-dominated era, and basically I could explain this as when energy density is greater than matter density. Now you might think to yourself, well then why isn't it called the energy-dominated era? Well, that's because of that energy, radiation was most prominent, hence the name. So let's move on to the next era, the matter-dominated era, and we'll take a look at a chart. Now as you see, these lines are going down. They represent radiation and matter. And as you see, the radiation line, although it's decreasing in density, it decreases faster than the matter density. And this is because radiation is a form of energy. Light is a form of energy. I shine it here on the board, and it's pretty strong. I shine it over there, and it's pretty weak. That's because as energy moves further and further away from the origin, it gets weaker, therefore exponentially decreasing its density. Now matter, on the other hand, matter doesn't get weaker as it moves away. Now, how come? Well, that's because here's a water bottle. Here's matter. Right here it's a water bottle. Over there it's a water bottle. It hasn't gotten weaker just because it's gone across the room. So with this in mind, you can understand how energy, because it's getting weaker, decreases faster than matter. And therefore, we move into the matter-dominated era. Let's move 380,000 years after the Big Bang, 2 times longer than humans have been around. At this point, things have cooled down enough for hydrogen and helium nuclei to be able to capture electrons. And then from this, hydrogen and helium clouds form. Now let's take a look at a picture from the WMAP satellite. Now this is a picture of cosmic background radiation. And to understand that, you need to know something about when you look up in the night sky. When you look up in the night sky and you look at any celestial object, it's emitting light and you're seeing that light. However, it's taking that light some time to reach you. It's taking the speed of light to travel here to reach you. But the speed of light isn't infinitely fast, so you're actually looking into the past as the light you're seeing. So if you look further into space, the further you look, the further it takes that light to, the more amount of time it takes that light to reach you, so that for the further back in time you're looking. And this is the first light. This is the first light 380,000 years after the Big Bang. And this, what you see on the screen, is representing the hydrogen and helium clouds. You'll notice the red portions and the blue portions. The blue portions are about 1/1000th of a degree cooler than the red portions. And the thing about the red portions and the blue portions is where it's red, it's hotter and it's also more dense. Now you need to know something about gravity. Where there's more things and there's more density, there's more gravity. So therefore, more gravity starts pulling more and more objects in. So eventually, these red spots will pull more and more stuff in because there's more density there. Eventually, till these spots start expanding and they start getting more dense and they start getting hotter. Do this for about 100 million years. And then finally, protons start combining in all sorts of ways. There's a huge release of energy and stars begin forming. And then, over the course of billions of years, more and more stars begin to form. And this is essential for the creation of everything else in the universe. Now, why is that? Well, that's because when a star dies, it releases a huge amount of energy, and within that energy, protons combine in all sorts of ways and create things like elements, create things like the periodic table of elements. And then those elements clump together and create bigger things like dust particles, like rocks, like moons, like planets. And then where those moons and planets and stuff are, there's more density, more gravity, so more stuff gets pulled towards them. Solar systems come together, and then solar systems clump together, form galaxies. Galaxies clump together, form clusters. Clusters clump together, form superclusters. And here we are today looking at billions of galaxies. Now, this isn't some CGI, some thing an artist made. This is a real picture taken from the Hubble Space Telescope. And each point you see here is not a star, but rather a distant galaxy with billions of stars, with billions of planets. So it makes you think, are we really that special? Now, as I've been mentioning, the universe is expanding, and you could think of it as a balloon. You put dots on it, you blow it up, those points expand, and they also move further away from each other, just like our universe. And they're created these gaps. And right now, presently, those gaps make up 90% of our universe. Now that's a problem because it defies the laws of physics. Because here is a spiral galaxy. It's spiraling around at an extreme velocity, and the problem with that is 90% of this is nothing, supposedly. And there's 10% that we could observe. Of that 10%, there is not enough gravity to allow these things to clump together. In fact, at such a high rate of speed and such little gravity, these things should fly apart, but they don't. So that must mean that that other 90% we can't observe, there has to be something there. There has to be something called dark matter and dark energy, which we can't see. And it takes up all these gaps. And that brings us to the dark energy dominated era. Theoretically. I say theoretically because, as we said, we can't observe it, so we can't prove it's there. So maybe we made a miscalculation somewhere, and the dark energy and dark matter doesn't exist. If that's the case, we'll still be in the matter-dominated era. But we don't know. This is what we think right now. And that brings us to 13.7 billion years after the Big Bang, today. So let's just review what we've gone through so far. So we have cosmic inflation, then we have protons forming, helium and hydrogen nuclei. The first stars are born 100 million years after the Big Bang. Then we have the earliest known galaxy, star formation at its peak, cosmic expansion beginning to accelerate, solar systems forming, and here we are 3.7 billion years later today. But what of after today? What of the end of everything? The end of the universe? Now, as I just discussed, we can't even explain dark energy and dark matter. So how are we supposed to explain something that's so far off, billions and billions of years from now will be the end of the universe? How are we supposed to explain that? Well, we can't. We can only theorize about it, and there's three theories. The first is the Big Freeze, the Big Rip is next, and then we have the Big Crunch. And these are listed in order of likelihood. So this one is the most likely, this one is the least likely. Now, these could be a whole presentation in itself, but I'm just going to touch on them briefly. So the Big Freeze, basically what this is as I mentioned, as things move away, as energy moves away, it becomes weaker. So eventually, the energy in everything will have expanded so much that it gets so weak that it can't fuel any processes of life of any form anymore. And things will just begin to die out because it's so weak. And then eventually, the whole universe will cool down to a value of absolute zero, and that will be it. That will be the end. So what about the Big Rip? This is basically when, as Hubble noted, that everything as it expands, it's expanding more and more rapidly. So eventually, all the galaxies and everything within them will start moving apart from each other at the speed of light. And then where do you go after that? You go faster than the speed of light. And then at that point, atoms will begin to rip apart. Everything will begin to rip apart and tear, hence the name the Big Rip. And that will be the end of the universe. Finally, we have the Big Crunch. This one is theorizing that basically, as everything moves out and it expands, it will eventually get to a threshold where it has to stop. And then at that point, it will linger a little bit. But then finally, all the gravity and mass and stuff will begin to condense and contract in on itself, and it will get smaller and smaller, and everything will get pulled back together into that one tiny point I mentioned earlier, that one singularity. And then maybe just maybe, this whole process will start again. Thank you guys for listening. If you have any questions about the Big Bang or anything else I talked about, you could ask me, you could ask Julia or David, and thank you guys.